we said that, okay, we will estimate or we will use some typical current loading values. So where these typical values are coming from, okay, and what is limiting us? Why, if we want to use a larger value, let's say, because these are typical values are usually decided without considering the power density concept. That's what we talk about, right? We want our machine to be smaller, compact, right? So if we want to make it compact and smaller, we may want to put more current than what conventional design is doing. But we cannot just keep increasing unlimited, right? There are constraints. So what are those constraints? One is this current density coming from, in fact, your current per meter square concept, right? The current density that is we are more familiar, the J value, okay? And it also depends on your slot dimension. So as we said, if the dimension of the slot also cannot be random, okay? So you have decided the air gap diameter, you have decided an outer diameter, and you have decided a certain number of slots, okay? So diameter 2 pi d divided by slot number gives you the area of your slots, right? Now, if you decided that I will have a certain number of slots, but you are going for a smaller size, so you will have a less diameter, which means that your slots are very narrow or very small. So your slot area is smaller, right? So if your slot area is smaller, first thing you need to see whether can you fit your conductors there, okay? You have decided a certain number of turns as well, okay? And a conductor size. So you have to see whether you can fit them in or not, okay? And so that itself actually comes from the conductor size itself is coming from actually your current density J, right? Because the current, when you select conductors, they are associated with current density J value. If you look at data sheet of conductors, they will tell you what is the current density it can withstand. And but that current density JRMS, which can come from conductor's data sheet, multiplied by the slots dimension. Okay, so slot dimension, how are we defining is what is the depth of the slots? Okay, D is your depth of the slots, and width of your slot is TS TS is the slot width and TT is this tooth width, okay? TS plus TT, these two together, is also determined by how many slots you have and what is your perimeter, right? How much, what length available to you. So current density multiplied by that dimension is basically also your current loading that we have determined, a meter per meter, okay, AS, current electrical loading, theoretically. But in fact, you cannot also cover the available slot area fully because you are inserting conductors there, right? And winding, the machine winders, they prefer, it could be done with some kind of automated machine, the winding, or it could be done by hand. Some, I think, machine winders, they prefer not to fill the slot fully because it's very difficult. If it becomes if it start to become very crowded, it's very hard for them, okay, to insert conductors. So they tends to leave a lot of space in the slots, okay. And if it's automated, Now, automated is kind of like, what is it called? You, in the swing machine, that the sort of things you like have a conductors are around something and then they insert it, right? So that also, even automated machine also tends to leave a lot of space in the slot. So the factor by which the slot is left empty is referred as the slot fill factor, okay? And so slot fill factor typically for the conventional distributed winding is about 20 to 30%. Okay, so only 20 to 30% is of the slot area is covered. Okay, concentrated winding can push this to up to 40%. Okay, some of the concentrated winding. So let's say if you push very much to your winder, you may fill it up to 40% maximum. Okay, so we are not utilizing the slot area fully. And on top of that, when the conductors are close to each other, the carrying current, they are the main source of your heat in the machine, right? And so that also determines how much current density you can push through it, okay? If you are not using any type of external cooling, then it is the lowest current density you should choose, right? So this is again a typical value, 4.5 to 6 current density when there is no additional cooling. If you are aggressively cooling it, then you can go up to 20 ampere per millimeter squared. Okay. So these are again actually typical value, but some of the machines are so aggressively designed that they are pushing this value to even 40 or even higher. Okay, so do not limit yourself to these values. These are only an indication for conventional machines. Okay, if you are using higher than these values, you should always ultimately check your thermal performance by doing thermal analysis of your machine. Okay. So, but as a starting point, obviously you can use these values based on what type of cooling you are going to use in your machine. And you can also see how they are linked to the power rating of your motor, your electrical loading of the motor, and your pole numbers. Okay, larger the pole number, smaller the current density, J. Okay, higher the power, smaller the current density. Okay, because higher the power means higher the current. Higher the current means you are using thinner conductors. Okay, so the density also becomes lower. Current density becomes lower. Then, so that's these factors, the mostly cooling is your limit on deciding what electrical loading you can use in your machine. Okay, that's your limitation. And then slot area, obviously. Then the second one is the air gap flux density, right? BZ. We said, okay, we'll use 0.8 or 0.85. Why not 1? Why cannot I use 0.9, right? Because there is again a limit. Okay, so what is that limit is basically in the, let's say this is your slot and this is your teeth. Okay, the next part is your teeth. This is slots and this part is called teeth. So usually when the flux passes, the highest flux passes through the teeth, because that's the iron part, right? Slot is air and conductors, copper. So permeability of copper and conductor is similar to air actually. So magnetic flux prefer to go through iron, so they prefer to go through the tooth. So tooth could become highly saturated. Okay. Now, the material that you are using to make your stator core, remember our BH characteristic, right? It has certain saturation limit, right? Something like this. That was your saturation. So tooth may be able to handle a saturation value based on your material property, right? The material that you have used. If it is higher than what it can withstand, then actually this is impractical. Nothing, what you are getting in your finite element or your analytical model is not going to accurately represent it. Also, if it is highly saturated, your machine may not perform as you are expecting because it is moving toward this non-linear region, right? So you may start seeing a lot of non-linearity in your performance that is not matching with what has been predicted, okay? So you want to avoid too high saturation. So there is a limit on how much saturation you should allow in your tooth flux density, okay? And of course, it also, the flux density, if it is too high, it can also lead you to high core loss, right? Because your core loss is basically square of the flux density times square of the frequency, right? So higher this B, flux density, also means higher core loss, okay? So that all may put some limit. And what is the saturation that you are expecting, or what is the flux density that you are expecting in the tooth can be calculated from the slot and tooth dimension, the slot width TS over tooth width TT time the air gap flux density is a fundamental component. So if you have decided, okay, it's going to be 0.9, let's say, and you calculate out what is this ratio, you have already decided dimension of your slots, so you can find out what is you are expected tooth flux density. And if it is exceeding the value that you can allow for the material based on its BH characteristic, that means either you have to reduce this BZ or you have to increase your slot width. Okay, that means you have to, tooth width. So you may have to increase tooth width, but then you have to reduce your slot size. Reduction slot size means your current density is affected, right? So it's all interlinked, all right? So that is, those two are related to electrical loading and magnetic loading. And the third issue we must consider is the mechanical or stress that is seen by the rotor, okay? It's known as shear stress, and this is the linear force over area seen by the rotating rotor, okay? Shear stress. And here again you can see some typical values for a typical conventional motor, okay? In fact, this shear stress becomes a very important parameter when you design motors for high speed. So we design one PM motor for as high as 100 kilo RPM, right? 100,000 RPM. So for that type of speed, the shear stress on the rotor is one of the key parameter, because if we do not work within the allowed limit of the material, your rotor can burst out, okay, break down mechanically, okay? So for high speed, shear stress becomes a very important parameter. And in case of IPM machines, in the rotor usually, let's say I just take a conventional IPM. This is your, this part is iron, and this is usually highly saturated. It's called a breeze. IPM machines breeze, okay, iron breeze. And mechanically it is very thin. Okay, imagine it's a piece of lamination, and you have, this is kind of like a hole, okay, where you will be inserting your magnet. So this part is thin iron piece, and the stress seen by this part of the rotor is the highest. So if you are designing for high speed, you should check what is the maximum stress that is occurring here, okay? And it must be within the limit of the material, okay? All material data set, you will find what is their withstanding capability. It's usually given by their yield constant, okay? Material data sets should have this information. It also another parameter is, it's called torque per volume, okay, TRV. So torque per volume is important when you are making machines small, compact, because you are trying to reduce the rotor volume compared to required torque or power, right? Through this derivation here, it can be shown that torque per volume, rotor volume, TRV, is proportional to that shear stress that we talk about. Okay, so this it's starting from the sizing equation of the torque, and then TRV's definition, which is output torque over rotor volume. So output torque is from our sizing equation divided by the rotor volume, and if we put all our parameters there, that these coefficients values there, it can be shown that in fact TRV is proportional to the maximum shear stress that we have defined in the previous slide. Okay, winding factor, electrical loading, magnetic loading over root 2 is the shear stress. And how do we get it? It is the output torque per radius divided by rotor swapped area. That's how it is defined. Okay, and from there, again using the same sizing equation, we can show that shear stress is proportional to electrical loading and magnetic loading. And here we can find that TRV is proportional to shear stress. Okay, so if we reduce their volume too much, rotor volume too much, this value is going to go up. Okay, and if this value is not within the allowed limit of the material, then your design is no longer mechanically possible, actually feasible. Okay, so you should check this TRV when you design, even if it is not for high speed. Okay, because if it is exceeds this material property, then it will not be practical. Okay. So here you are seeing again some typical TRV values for different type of motors. Typically for liquid cooled machine, it is the highest because you can use a smaller volume or high current density if we have aggressive cooling. Okay. The other thing is, like, we have talked about pole numbers, right? We said that pole number we can either decide in the beginning, or we can determine or optimize. Now, it can be seen that if you have larger pole numbers for the same motor, you can reduce the size, as it can be seen here, but also at the same time, the width, this width is known as the yoke width, right? The width from the outer diameter to the where the slots are. Okay, top of the slots. So this becomes thinner and thinner. Okay, so if it becomes too thin, it may be again not practical. Okay, it may become impractical, or it may become impractical to build manufacturability. Why it reduces can be quite easily understood, because your air gap flux, once it goes to the yolk, it divides into two flux, right? So the yolk sees half of the air gap flux actually, right? And from that relation, actually, we can find how the flux density here depends on the pole numbers, and pole number inversely related there. This width here is inversely related to the pole pairs. Okay, just from this quite simple relation. All right, and so this one, I think this work was done by Professor J.Q. Ju from Sheffield. So I may have the reference later when I provide the reference list. You may, if you want to read that paper, if you can, okay, to understand better what it is and how it is. Also, your pole pairs, higher the pole pairs, remember that it also affects your frequency. Okay, because your frequency pole pairs are synchronous machines, so synchronous speed, they are related, inversely proportional, right? And also your speed. Higher the speed you may have, and if you have higher pole pairs, you will end up at a very high fundamental frequency. If you have very high fundamental frequency, your switching frequency in the inverter may not be sufficient, right? So again, I can give you an example of that, our 100,000 RPM motor. So that 100,000 RPM, it has 4 pole, and fundamental frequency of that motor is like 3.3 kilohertz. Okay? If fundamental is 3.3 kilohertz, you definitely need a very high switching frequency, right? 5 kilohertz will not do. 10 kilohertz will not do, okay? So that also should be considered when you are determining the pole pairs, okay? The frequency, will it be feasible with the inverter that you are planning to use with switching frequency? Is 10 kilohertz or 5 kilohertz sufficient or not, okay? And high frequency also could lead you to higher AC resistance loss, right? What we talk about. So that also should be considered, because you may end up, if you do not consider AC resistance, you may end up lower efficiency than you have predicted. Okay, high frequency, high speed. So all those issues can come up. So this is an example. As I said, we'll look at an example here. How what we have talked about, how it is done. So I will show you something here. I think the parameters. Okay, this set of parameters are given. Okay, let's say as a numerical example, if you want to try out to do how to calculate all those things numerically. So this set of parameters, we have the air density of the typical air density, air drag coefficient, front area, maximum speed, that is related, that is we are for the car, let's say, weight of the car, gravitational constant, rolling coefficient, wheel radius, acceleration time, and differential gear ratio. Okay, this is of a typical car values. Okay, from a I can't remember where it was, which car it was from, maybe Tesla or something. Okay, these values were taken for a typical electric car. Okay, and then this sort of parameters will be available easily for you to find. Okay, now we using this first part is for us to calculate out the traction force, right, as we talk about. So going back here, we will calculate out our traction force, okay? In the traction force, like remember, we talk about that we may consider this part, which is related to inertia or acceleration, only for peak power, okay? But for the rated power, we may even neglect this part to calculate the rated power. So rated power is mostly your the rolling resistance and the drag, okay, air drag. So we can calculate from there, and if we know the DC bus voltage, as we said, we can find out what will be our peak rated voltage. So we will know what is the peak rated EMF, and that from there we may be able to calculate the turns, okay? So here, just showing you some calculation that power for this particular machine of particular car was found to be 73 kilowatt. Torque is 56 Newton meter. This is just without the acceleration part. And then after changing it to or using the gear ratio, okay, after using the gear ratio. And then the peak torque is also calculated. When we calculate peak torque, the acceleration force is considered now and added together. So peak torque is 247 compared to 56, okay? Peak torque is nearly 4 times. And usually they ignore this force related, gravitational force related to the slope, okay? Because this is like you do only rarely, and it is assumed that for that short period, that the peak torque that we are considering should be sufficient also to handle that force, okay, for short term. So once we have this torque and power found, the next is we go for our equation, sizing equation, okay? And this part I have left for you to try out, okay? We calculated the force, and then you try to see whether you will be able to estimate what is DZ and what is LE for this particular machine or motor. And you can even use that to use as a example case for your finite element, okay? But one thing we should know that so far it's all we have done is analytically calculated, right? And as we discussed previously, that we haven't considered any saturation or any like the the magnetic saturation. We have ignored any kind of leakage, flux, etc. Right? This is like all in our estimation. We just ignored all those things. So from here onward, we could use to check the performance again analytically if we wish, because there are analytical models for motors performance calculation. So we could use analytical method to find out what is the air gap flux density for this geometry, okay? Am I getting 0.85 or 0.8 that I have assumed? Or is it the torque that I am going to get from this machine? So you can do analytical calculation further for performance verification, okay? There are a lot of papers on the analytical model as well, but they are never accurate. okay, because they again cannot consider saturation and leakage. So, and they end up having your overestimation. Okay, but they could be good just if you want to adjust things at this stage before moving to finite element. They could be good tool to check your initial base design's practicality. Okay. But for more accurate results or more accurate performance analysis, we have to use finite element. So next part will be just going through a bit about finite element work. Okay. Any questions so far? Okay. All right.